In this video, we're going to take a look at the fundamental theorem of calculus. This is just a refresher from hopefully what you learned in Calc 1. So we're not going to go through the entirety of the fundamental theorem of calculus. We're just going to look at the big points and how to use it. So in the previous section, we used a definite integral, and that definite integral symbolized signed area. In this section, we want to figure out that signed area of a fairly nice function. Now, there's a lot of weird functions out there, but when functions are smooth and continuous, then we'll have a nice function, and we want to find the signed area of those types of nice functions. So the fundamental theorem of calculus says if we let f be continuous on a closed interval from a to b, and we let capital F of x be the antiderivative of f, that is lowercase f, then if I want to integrate lowercase f from a to b, I can take the antiderivative, plug in b, subtract taking the antiderivative and plugging in a, and that will give me the definite integral. So, in other words, the signed area can be found by a difference of antiderivatives. Now, f needs to be continuous. It also should be smooth. We want to have a single antiderivative for my lowercase f. So it has to be continuous, and I have to be able to find an antiderivative for this to work. But if we have a nice function that has those properties, then the fundamental theorem of calculus will work. So this is a great way to find signed area or to find the definite integral. Now, this is really, really big. Remember, anything that's called the fundamental theorem of something is going to be a huge deal. Fundamental, as a word, is foundational. Being able to find signed area, find definite integrals using antiderivatives is really a huge thing. So let's go ahead and do that on an example that we dealt with in the previous section. Let's take the definite integral from 0 to 3 of 2x minus 1 with respect to x. Now, as we're doing this, I will introduce you to some new notation, but first, I want you to understand that the antiderivative of 2x minus 1, well, that's going to be x squared minus x. That's one antiderivative. You could add technically any constant that we wanted, but I'll just use this one. Okay, I'll show you what happens when we don't do that. So this definite integral can be found. Let me copy and paste. Excuse me. So this definite integral can be found by taking f, capital F that is, of 3 minus capital F of 0, where we're using this f. If you plug in 3 squared minus 3 gives you 6. When I plug in 0 squared minus 0 gives me 0. So f of 3 is 6. f of 0 is 0. 6 minus 0 is 6. So the definite integral from 0 to 3 of 2x minus 1 with respect to x is 6. Now we calculated that in the previous section using geometry techniques. So this is a lot more efficient and a lot more algebraic. And the bonus of this fundamental theorem of calculus is that when we get into definite integrals where we can't calculate using geometry, well, that fundamental theorem of calculus allows us a way to do that. Now, here I used capital F notation. A lot of times, instead of using that type of notation, what people will do is they'll use various types of, how would I say, various types of integration notation. So what's going to happen is when we have a definite integral, we know that one of the antiderivatives is x squared minus x. To indicate that I need to plug in 0 and 3, oftentimes what will happen is we write the antiderivative in a bracket and we'll put the 0 and 3 kind of as subscripts and superscripts of that bracket to remind us that we need to plug in 3 and we need to plug in 0. Some people will use x equals 0, x equals 3 as subscripts and superscripts of the bracket. Some people will use a straight line as well, and at the bottom of the straight line they'll use 0, top of the straight line you'll use 3. Lots of different ways to do that, but essentially this is the notation that I'll use the most. Put the antiderivative there, subscript of 0, superscript of 3. And in the next step, a lot of people will go in brackets, 3 squared minus 3. That's what you get when you plug in 3, minus in brackets what you get when you plug in 0, 0 squared minus 0. And when that's all calculated, you get 6 again. So that's one way notationally to do that. So antiderivative in square brackets, subscript, superscript. Usually if I'm writing it by hand, that subscript goes even lower, the superscript goes even higher. Okay. But we get 6 in any case. This is a good time to point out that the reason that you can use any antiderivative you want is that when you plug in 3 and plug in 0, if I did have a constant, let's say I had a constant of 11, for instance, what would have happened when I plugged in 3, I would have gotten a plus 11, and then over here I would have also gotten a plus 11. But this plus 11 and then minus this 11 would have canceled each other out and I would have gotten 6. The same with this notation, I would have just gotten 6 plus 11, so I would have gotten 17. And then I would have gotten 11, which is 6. So no matter what constant you add, it's going to cancel out with this subtraction here. And that's why oftentimes we will let our constant be 0 because that's the easiest one to deal with usually. So letting that constant be 0 for the antiderivative. So that's how we can use the fundamental theorem of calculus. And like I said, that's a really, really big deal, this result. I'm not going to show you how you get this result. It comes from dealing with Riemann sums. And since this is just a refresher on fundamental theorem of calculus, we won't go in and prove it or anything like that. But again, it's a really big deal, has to do with limits and how limits work with the Riemann sums. Now, the advantage of the fundamental theorem of calculus is now we can find definite integrals no matter what our function is. In our previous example, we had found the signed area using geometry. In this one, I could get approximate signed areas using Riemann sums, and then if I took the limit of Riemann sums, I could find the area. But with the fundamental theorem of calculus, this function here, which is not accessible via geometry, I can find this definite integral, so this signed area, without having difficulty. So we can just use the fundamental theorem of calculus to find the signed area. Let's go ahead and do that. Okay, so here we go. First thing I have to do is find an antiderivative. Doesn't matter which one, but I'll use the antiderivative with 0 as the constant. So we get 3/2 x squared minus 1/3 x to the third. And then I'm going to plug in 0 and 3 as my bounds. It's not always going to be 0 and 3, but in this case it is. If I plug in 3, all I have to do is take 3/2 times 3 squared minus 1/3 times 3 to the third. That's what I'll get, whatever I get when I plug that in. And then when I plug in 0, that's 3/2 times 0 squared minus 1/3 times 0 to the third. It's often nice to plug in 0 into a polynomial. When we take 3/2 times 3 squared minus 1/3 times 3 squared, 3 to the third, excuse me, I get 4.5. So I get 4.5 when I compute this one. And I get 0 when I compute this. So 4.5 minus 0 is 4.5. So this definite integral turned out to be equal to 4.5. That means the signed area here is 4.5. So when we're going from 0 to 3, you'll notice that, excuse me, my graph is 3x of y equals 3x minus x squared, or f of x equals 3x minus x squared is here. From 0 to 3, all of that is above the x-axis. So the signed area I'm looking at is this shaded region here in blue. And this shaded region does not have straight lines. It's obviously parabolic, and therefore it'd be really hard to deal with in geometry, using geometry tools. But with the fundamental theorem of calculus, it's easy to calculate the fact that this area is actually 4.5. So the fundamental theorem of calculus is a really, really nice tool. Let's do another. Let's find this definite integral using the fundamental theorem of calculus. We are going to integrate x squared plus 2 with respect to x from 1 to 5. So let's go ahead and do that one. Here we go. So obviously, if you want to try this on your own, you can push pause on the video and then try that on your own. But for me, I'll do this right now. So integrating from 1 to 5. First thing I need to do is find the antiderivative. That's going to be 1/3 x to the third plus 2x. And I'm going from 1 to 5. Again, the notation that I use is subscripts and superscripts around a bracket, and in the inside of the bracket contains some antiderivative, usually the antiderivative with 0 as the constant. So we're going to plug in 5, 1/3 times 5 to the third plus 2 times 5. We're going to calculate whatever that number is, and then we're going to subtract whatever number I get when I plug in a 1. So 1/3 times 1 to the third plus 2 times 1. I'll do this in a couple of steps. So 1/3 times 5 to the third power plus 2 times 5. That gives me 51 2/3. When I take 1/3 times 1 to the third power plus 2 times 1, I get 2 1/3. And if I take 51 2/3 minus 2 1/3, I get 49 1/3. So 49.3 repeating, or 49 1/3. And that's the signed area for this function from 1 to 5, x equals 1 to x equals 5. I'm not going to graph that because it's not needed, but we see, hopefully, we see now how this is all calculated. Sometimes people will put these numbers, the 51 2/3 and the 2 1/3 in parentheses or in brackets. That's perfectly fine too. Again, there's a couple of different notations here. The notation I like to use is antiderivative inside the square brackets, and then I superscript and subscript the bounds. Notice that the bounds, we're no longer integrating. I lose my integration symbol, and I put the bounds on the right-hand side instead of the left-hand side because I don't want to think I need to integrate again. So that's the usual notation. Now let's do another example. This time, let's integrate sine of x with respect to x from 0 to pi. Now, normally, anytime we're dealing with calculus and trig functions, we're going to be using radians. So when we do this, we're going to make sure our calculator is in radian mode if you are utilizing your calculator to figure out the answers. So just a little hint, anytime you're doing calculus with trig functions, our standard derivatives, our standard integration rules will apply to those trig functions when our inputs are in radians. If our inputs were in degrees, we'd have to change the standard rules for sines and cosines. All right, so dealing with sine here, and because we are dealing with sine, and we're dealing with radians, so again, our antiderivative of sine we know is negative cosine of x. We're going to be plugging in 0 and plugging in pi. And what I was saying earlier is that since we're using radians, make sure your calculator is in radian mode. But taking the antiderivative of sine to be negative cosine is reliant upon us using radians. So our standard rules for antiderivatives, our standard rules for derivatives with sines and cosines are reliant upon us using radian measure. And if you use degree measure, you'd have to change those derivative rules and the antiderivative rules. Okay. All right. I'm just going to calculate this. When you plug in cosine of pi, you're going to get a -1. So you get negative cosine of pi, which is the negative of a -1. When you plug in cosine of 0, you get a +1. So what this is, oops, in the first parentheses, this is a negative of a -1. So negative of a negative is a +1. And then you get minus -1. So again, subtracting a negative. So what this tells me is that if I integrate sine from 0 to pi, I'm getting 2. That's a very nice whole number to deal with. And it's probably fairly surprising as well. If you think about the sine curve, it's this weird trig curve here. And you wouldn't think that the signed area is going to turn into a whole number. But it does turn out that if you go from 0 all the way to pi, and we want to find this area, it turns out that that area is exactly 2 using the fundamental theorem of calculus. And that is, again, fairly surprising that this area in blue turns out to be a whole number. Let's do another. Let's say we want to integrate 1,800 e to the 0.12x with respect to x from 0 to 5. So let's go ahead and do this. I won't graph this one, but we will just use the fundamental theorem of calculus to figure it out. So here we go. Oops. The antiderivative is going to be e to the 0.12x, and then I'm going to have to divide by 0.12. So I'm going to take 1,800 divided by 0.12 as my coefficient. I could add a +0 if I wanted to as well, but I'm not going to write that down. If I take 1,800 divided by 0.12, that actually gives me a nice value out front, that gives me 15,000. So I get 15,000 e to the 0.12x, and then I'm going to plug in 0, plug in 5, and figure out what I get. So let's start by plugging in 5, 15,000 e to the 0.12 times 5 minus what I get when I plug in 0. Now, be careful here. This is not a polynomial. So when you plug in 0, you do not get out 0. Polynomials, when you plug in 0, you get out a 0 often. But in an exponential function, this is going to be e to the 0, which is going to be a 1. So we'll do both calculations. Take 15,000 times e to the 0.12 times 5. That's 27,331.78. This is not going to be an exact, so since this is going to be an approximate answer, I'll just put it as approximate. And when I plug in 0, 15,000 e to the 0.12 times 0 gives me 15,000. Again, e to the 0 is 1, so this thing turns into a 1. I just get 15,000 times 1. When I do the subtraction, that's 12,331.78. Now, this is rounded to 2 decimal places. In our class, I usually ask that people round to 2 decimal places, round their answer to 2 decimal places, if need be. So that's the typical thing we do in the class, in our class. But other people may want you to go out to 3 or 4 or 5 decimal places, or maybe even 1 decimal place, or might be the nearest whole number too. In any case, this is the answer rounded to 2 decimal places. So we can use the fundamental theorem of calculus on lots and lots of different definite integrals. Now, another nice thing about using the fundamental theorem of calculus and calculating definite integrals is that now in modern times, there are lots of different technology programs that will allow us to calculate the definite integral. In particular, the one that I use often in this class is the TI-84. So on the TI-84, there is a math button on the left-hand side. And if you just hit that math button and scroll straight down to number 9, you'll see an FNINT. And that allows you to do definite integrals. That allows you to integrate functions. Now, I will try to post another video and just show you explicitly how I'm plugging things into the TI-84. So if you want to look at that, you can look at that. But for right now, what I'm going to do is I'm just going to talk through how to do these. So for instance, we can go back to examples 4 and 5, and we can simply type in, again, it's in the math 9, and then when I pull it up, it gives me the integration symbol. So we're going to integrate from 0 up to pi, and then I hit sine of my variable x with respect to x. And if I do that using technology, I also get a 2, just like when I did it by hand. I could have also used technology to compute this one. I could have integrated from 0 to 5, 1,800 e to the 0.12 times x dx. And again, technology gave me 12,331.78, just like we got by hand. Again, I'll try to post another video of how to actually type things into the calculator. But on this video, some of you already know how to do that, so I won't spend my time on this video doing that. If you don't know how to do that, then watch that other video that I've posted. Now, that turns out to be really nice and a big time saver in many cases. So for instance, if I want to integrate 2x squared minus 5x minus 3 with respect to x from -1 to 2, I can do it very fast by just going and using my calculator, typing in that integration under the math function integrate from -1 to 2, 2x squared minus 5x minus 3. And when I did that, I got negative 10.5 as this definite integral. So the signed area was negative for the most part. It wasn't always negative, but so signed area total is a negative 10.5 for the first one. When I type that in to this one, when I go math 9 on my TI-84, 0 to pi over 2 of cosine of x with respect to x, I ended up with a 1. So again, this first integration using technology, I could just type it in and I get a negative 10.5. This second integration, I just type it in and I get a positive 1. Again, I'll show how to type on a separate video. Now, I'm going to use both technology, meaning my TI-84, and the fundamental theorem of calculus to compute this integration. And we're going to integrate from 0 to 9, the square root of x with respect to x. All right. Now, the first thing I'm going to do is I'm going to rewrite this into something that's nicer to integrate. So instead of writing that as square root of x, I'm going to write that as x to the 0.5. Notice I have not integrated yet, so I am keeping the integration symbol in front still. Now I'm going to integrate. And when I integrate, I'm going to raise the power by 1. I get x to the 1.5. And then 1 divided by 1.5 is 2/3. You could either write 1 over 1.5 or 2/3. Either way is perfectly fine. Guess I'll use that way. I'm going to plug in 9 and 0. And so that's what we do. So 1 over 1.5 times 9 raised to the 1.5 power minus 1 over 1.5 times 0 raised to the 1.5 power. Raising 0 to any power gives you 0. So that's a nice, usually a nice thing. So 9 to the 1.5 power, by the way, is 27. When I take 1 over 1.5 and then times it by 9 to the 1.5 power, I get 18. So I get basically 18 minus 0, not basically, exactly 18 minus 0, which is exactly 18. So if I do the fundamental theorem of calculus by hand on the square root of x integrated from 0 to 9, I get exactly 18. If I use technology, specifically my TI-84, and I just go and do math 9 integrate, it turns out my calculator gives me something very slightly different than 18. My calculator gave me 18.0000, lots of zeros, 25. Now, rounded to 2 decimal places, these two numbers are the same. But you can see that for some weird reason, the technology gave me a little bit extra above the 18. The reason that technology did that is because technology uses the technology from the TI-84 in particular, utilizes numerical algorithms to find that signed area. And sometimes those numerical algorithms are going to give us the exact values. Other times they're going to be just slightly off. Now, is that going to matter most of the times? Well, most of the times, if you're rounding to a couple of decimal places, it's not going to be off in any significant way. So utilizing the fundamental of theorem of calculus by hand or utilizing technology isn't going to throw you off a lot. But if you're looking for like an exact answer, we have to realize that sometimes when we use our calculator, that answer can be off just by a touch. So that's just a note I want to make, that technologies use numerical algorithms to find the area. In particular, the way our calculator does it uses those numerical algorithms to find the area. Sometimes that gives us the exact answer, but other times it will give us an answer that's really, really close to the exact answer. And so just be careful, be aware of that. If we're rounding to 2 decimal places in this class, then it usually doesn't make any difference. But in some cases, if you're trying to look for a specific answer and you are thinking it's 18.00000025 and it's actually precisely 18, then you may be off by a little bit. So that's it as far as a review goes. I will say this again for our class, that We will freely use that technology. And like I said, I'll post a video of how to integrate with the TI-84, and it'll be next to this video.